In the first of the videos for this master QG derivation, we accomplished step number one, which was to take the basic momentum equations that are familiar to most everybody from a first semester dynamics course in meteorology and to transition them, first of all, to pressure coordinates, so from XYZ to XYP. And we also wrote them or transformed them from Lagrangian form to Eulerian form by expanding the total derivatives and separating the advective terms from the local tendency terms. And then finally, we also simplified those equations a little bit by assuming frictionless flow. That'll be the first of several simplifications that we make throughout the QG derivations. The next step is to take those two component equations that we wrote down and to combine them into a simplified vector momentum equation. So these are the two equations from before, and the goal here is to combine these two into a vector equation. So instead of having partial u partial t and then a separate equation for partial v partial t, we're going to combine those two into one equation that is partial with respect to time of the total horizontal wind v vector for further analysis. So the terms on the left-hand side very simply will combine into the desired term, which is partial v vector partial t. And we can consider the terms on the right-hand side now step by step as we work through this to see what terms emerge out of the combination of these two equations. Starting off with the first terms on the right-hand sides of both equations, this represents the zonal advection here. And we can rewrite those a little bit into standard basis form as minus u partial xi hat, and then in the other equation, minus u partial v partial x j hat. And if you look at these two terms together, you notice that they both have in common minus u, and they also both have in common partial with respect to x. So the only difference here is that this term is ui hat and this term is vj hat. And those two will combine into the total horizontal wind v vector. So those two terms together, we retain the minus u, we retain the partial with respect to x, and we combine the ui hat and vj hat into v vector. The same two things can be done with the meridional advective terms here. We write them in standard basis form. Both of these have in common minus v. They both have in common partial with respect to y. And so those elements stay the same, and then the ui hat, vj hat combine into v vector. Now we've taken four terms and collapsed them into two, and we can take these two terms and collapse them yet again into a single term. What we have here are two things being multiplied together. The first element is lowercase u, lowercase v, which together is the v vector. The second element is partial with respect to x of v vector and partial with respect to y of v vector, which is just the horizontal gradient of v vector. And so those two terms will combine into the dot product of negative v vector with the horizontal gradient del sub h of v vector. For the third terms on the right-hand side of the equal sign here, this represents the vertical advective terms. And we can again write that in standard basis form. And we look at these and we see that they both have negative omega in common, and they both have partial with respect to p in common. And so those will combine into minus omega partial with respect to p of v vector. The next set of terms, the fourth terms on the right-hand side of the equal sign in standard basis form, we have minus partial with respect to x of phi I hat and partial with respect to y of phi j hat. So this looks like partial x, partial y looks like the horizontal gradient of phi, and so that collapses into minus del sub h phi. And then the last two terms, plus f times v I hat minus f times u j hat, those represent the horizontal components of the Coriolis force acting on the horizontal wind, and that will collapse into the cross product minus fk hat cross v vector. And that is it. So we've taken these two component equations, we've combined the terms where we were able to, and we've now written a vector equation where on the left-hand side we have partial v vector, partial t, and we have four terms, vector terms on the right-hand side that we can work with for further analysis. So we've accomplished now step two, which is to write down the simplified vector momentum equation from the component momentum equations. The next step in the process will be to take that equation and partition it into geostrophic and ageostrophic parts in order to write down the QG vector momentum equation. And that'll involve some additional simplifications using scale analysis. But before we even get to that, it's worth at this particular point pausing to consider the physical meaning and interpretation of the terms in the simplified vector momentum equation that we just wrote down. And I'll do this several times throughout this entire process of deriving the QG framework, just so that we don't forget the physical meaning of a lot of these terms as the equations continue to get more and more complicated as we work our way down through the process. So this is what we just wrote down. We have partial v vector, partial t on the left, and then these four terms on the right-hand side. So the physical meaning of the terms, first of all, on the left-hand side, the term partial v vector, partial t just represents the local change in the horizontal wind. On the right-hand side, the term negative v vector dot del sub h v vector represents the horizontal advection of the horizontal wind. And it's worth pausing here for a quick moment to better define the term horizontal as it relates to our isobaric coordinate reference frame that we are working with here throughout this process. So in the isobaric coordinate system, the word horizontal, strictly speaking, is relative to pressure surfaces and not to height surfaces. So as a crude example of what that would maybe look like, if we look at an XZ cross section and we draw on an undulating pressure surface here where the pressure is constant along this wavy surface, the horizontal dimension, strictly speaking, would be the dimension that is parallel to that pressure surface. So horizontal actually would have a little bit of an undulation to it that matches the undulation of the pressure surface. We won't dwell too much on that, but strictly speaking, that's what we mean by horizontal when we're using that, that subscript in these equations. So putting that aside, we can, considering just terms 1 and 2, look at how those two terms affect one another by using a fairly simple example. And we ask the question by using this case here at the bottom where we're looking at x and y in a cross section, so just a horizontal cross section here, where we have winds that are blowing from the southwest that are stronger in the southwest corner and weaker in the northeast corner of this diagram. We can ask the question, is the local tendency of the horizontal wind, so partial V, partial T, is the local tendency of the horizontal wind positive, negative, or zero at the blue dot right here in the center, due solely to the effect of term 2 being the horizontal advection of the horizontal wind. So to do that, we take term 2, written as the vector dot product here, and we rewrite it using the mathematical definition of dot product as the multiplication of the magnitude of the two vectors times the cosine of the angle between the two vectors. And we know from vector calculus that the magnitude, or the absolute value of any vector, is always going to be a positive quantity. So the magnitude of v vector is some positive value. The magnitude of the horizontal gradient of v vector is also going to be some positive value. Now, the big question will be, well, what is the sign of cosine theta in this particular equation for the case as illustrated in this diagram here to the bottom? So first of all, we can assign a direction to v vector. So which way is the wind blowing from? Well, the wind is blowing from the southwest everywhere in this diagram, and so v vector points toward the northeast. And as far as the direction of del sub h v vector, in which direction is the horizontal wind getting larger? And it's obviously getting larger with southwestward extent across this picture, and so the horizontal gradient of v vector points toward the southwest. So the cosine of theta, theta represents the angle between these two vectors, and the angle between the green vector and the pink vector in this picture is clearly something about 180 degrees, and the cosine of 180 in degrees would certainly be a negative value. So we know the sign of cosine theta is going to be negative. We also have a leading minus sign on the right-hand side here, and so taken all together, the multiplication on the right-hand side of the equal sign here, we're multiplying a negative times a positive times a positive times a negative, and so that works out overall to be a net positive on the right-hand side, which suggests that since the horizontal advection of the horizontal wind is net positive, that means that on the left-hand side, that partial v vector, partial t, must also be positive. And that suggests that the horizontal wind, which is v vector, is increasing at the blue dot over the course of time. And that makes physical sense because we, looking at the picture, can envision the idea that faster winds to the southwest or higher momentum air to the southwest is being advected toward the blue dot with time. So imagine taking this entire wind field that we have pictured here and advecting it or moving it toward the northeast with time. So the wind at the blue dot gradually increases here over time, which is the physical meaning of the positive value of partial v vector partial t. So that is kind of how term 1 and term 2 interplay together. Then we can look at term 3, the next term on the right-hand side of the equal sign here. This physically represents the vertical advection of the horizontal wind. And so once again, we can put together a scenario to illustrate how that particular term would work and influence the sign of partial v vector partial t in this equation. So the scenario now is we have an xz cross section, so a vertical cross section through some slice of atmosphere. We have slower winds closer to the ground and higher winds as you go aloft. And again, we have a blue dot right here in the center of this vertical cross section. And if we assume that there is net ascent occurring in the image, so there's a tendency for the air to want to rise, if ascent is occurring in the image below here, is the local tendency in the horizontal wind, that is partial v vector partial t, positive, negative, or 0 at the blue dot due to the impact of term 3. So now we'll ignore term 2 and we'll only consider term 3 in its influence on partial v vector partial t. So once again, we'll write down the term and then assign signs to all of the various values in this term. First of all, we recognize here that pressure has a tendency to increase downward toward the ground. And if we assume that ascent is occurring in this image, as you go up, pressure would be decreasing. So the value of the, or the sign of the differential partial p here would be negative if we're going up. And as you go up, as pressure goes down, as we go up, what is happening to the value of v vector? The wind is actually getting stronger as we go aloft, and so the differential partial v vector is positive because as we go up, pressure is going down and v vector is going up. So we have a positive over a negative, meaning that the overall sign of the partial derivative partial v vector partial p is net negative. Now, what about the sign of omega? Omega is partial p partial t. So the change in pressure with respect to time. If the air is ascending in this image, pressure would be going down with respect to time if you're following an air parcel as it ascends. And a decrease in pressure with increasing time would suggest that omega is negative. And omega is always negative for ascending motion. And so the sign of omega would be negative here. And we also have a leading minus sign on this term. So we have a minus times a minus times a minus, which gives us a net negative sign for this term, given the constraints of what's being described here. And the negative implies that partial v partial t on the left-hand side, if term 3 is the only term acting, that partial v partial t is negative, meaning that the tendency of the horizontal wind is for it to get smaller with time. And physically, that makes sense in this particular case because slower horizontal wind from below is being advected upward to the level of the blue dot here. So that lower momentum air from below, because there's ascent occurring, that lower momentum air is being carried upward and is influencing the local tendency of the horizontal wind at the blue dot by making it smaller. So you would envision the entire wind field moving upward here and the winds at the blue dot getting less over the course of time. So that's term 2, that's term 3, and then we look at term 4, and we'll look at term 4 and term 5 here together on the right-hand side. Term 4, the physical meaning of this is just the horizontal gradient of the geopotential, and term 5 is the horizontal Coriolis force. So once again, we can do this graphically, and we have here an XZ cross-section again, and we've put on here a pressure surface where the pressure is constant along this undulating surface, and we have this blue dot that sits right here along that pressure surface. And we'll assume here that we're in the northern hemisphere. We will also assume that the geopotential field is uniform in the y direction, so this undulating pressure surface looks the same going both into and out of the screen. And we'll also assume that we have horizontally balanced flow. And with all of those assumptions in mind, which direction is the wind blowing from at the blue dot? So the first question we can ask is, how does del sub h phi point? And before we can assign that, we'll do a little bit of analysis on it, remembering first of all that phi, the geopotential, is just gravity times geopotential height, or times height. And gravity times height, we can look at the height of that pressure surface above the ground, and we notice that to the east of the blue dot, the pressure surface is closer to the ground. To the west of the blue dot, the pressure surface is farther from the ground. So z is smaller with eastward extent and larger with westward extent. And since g doesn't change anywhere, the larger value of z to the left suggests that geopotential is larger to the left, which suggests that the gradient of geopotential points to the left or points westward toward larger values in this image. However, and when we look at the term in the equation, we see that it's not del sub h phi, but it's negative del sub h phi. And so we take that term and we switch it to the other side. So negative del sub h phi actually points east in this image. And because we're also constraining this to be a situation of horizontally balanced flow, and we're above the boundary layer, we're assuming geostrophic balance. So the balance between the pressure gradient or the geopotential gradient is balanced with the Coriolis force. So if the geopotential gradient, the negative of the geopotential gradient points east, then the Coriolis force must point toward the west. And because we know that the Coriolis force always orients to the right of the wind in geostrophic balance, that would indicate that the wind is actually blowing out of the screen or from the north in this case, which makes sense because we have lower heights to the east, so a trough to the east, and we have higher heights or a ridge to the west. And we would expect there to be a northerly wind when you have a trough to the east and a ridge to the west in between those two. And that is the full analysis here of the QG, or of the vector form of the momentum equation. And the next thing that we will do in the next video clip is to take this equation and partition it into geostrophic and ageostrophic parts to write down the QG version of our momentum equation.